Well, let's sketch some curves. This lesson is sketchy. I'm sorry, I couldn't resist. For each of these, sketch a graph of the function as accurately as possible and then sketch the derivative. So let's just jump right in. I'm going to sketch the original function in blue. That's just how I'm going to do it. And then I will sketch the derivative in red. Sorry, you probably hear these pins rolling around on the desk. F prime of x is going to be 2. Let's just go ahead and jump straight in and find some derivatives. That's just going to save us a little bit of time later. We'll do this one as well. And that's equal to negative x minus 2. And we'll do this one. I'm skipping that one. I think that one's worth talking about at a later date or later in the video. Cosine there. And f prime of x is negative sine of x. There we go. And let's jump right in with this one. All right, the graph of 2x minus 1 is a y-intercept of negative 1, slope of 2, and without a ruler, I'm going to try to draw this as straight as I can. No promises about its complete accuracy, but that's the line 2x minus 1. Okay, I'm going to graph the function 2, just 2, right? So 2. All right, well, let's make an observation. The derivative of this diagonal line was a horizontal line. Put some arrows just for fun. And the slope of the blue line, the function itself, was positive. And because the slope is positive, the derivative, of course, is going to be positive. And so I drew something above the x-axis. Okay, so just a couple observations. So looking ahead, knowing that I'm about to draw a line with a negative slope, when I draw the derivative, I'm going to have a horizontal line that it's going to give me a line below the x-axis as a derivative. Sorry, I'm careful how I worded that, and I was afraid I was going to say something wrong, so I hesitated. All right, negative 3x is this right there. And whoops, I'm trying to get the pen just right, and it keeps bumping into the thing that's holding the camera. There we go. And so, again, back to the first one. Positive slope. The derivative is going to be, well, positive. And notice that the derivative is above the x-axis. Negative slope, no surprises here. This is common sense, but it's just worth pointing out now that we're seeing it in a graphical way. Negative slope, we're going to graph a derivative, and that derivative is going to consistently be below the x-axis because it is negative. Okay, so let's go to the absolute value of x, but it's actually negative absolute value of x, which gives us a graph that has a slope of positive 1 and negative 1. It would normally open upward like this, but because of that negative, it's going to open downward. There's this side of it, and there's this side of it, and we are going to graph it before we ever find a derivative, and I think that's just worth noting. Excuse me. The graph of the derivative, well, just look at the slope. You know, again, I could have looked at the slope here, and I could have said, oh, the slope is 2, so graph 2, like the line 2. So here the slope is 1, so graph 1. But I'm only going to graph 1 for these x values, the x values that are negative, because that is the only place where that applies. So we're going to do this, and I said only where it's negative, so not 0. We'll talk about that in just a second. And then over here we have a slope of negative 1, so we're going to graph the line, well, negative 1. So, well, negative 1. We're graphing derivatives, we're graphing slope. Okay, old lesson from way back. We are going to talk about whether the slope exists at that point, at the vertex. And knowing that the slope from the left is 1 and the slope from the right is negative 1, we actually don't have a slope that is defined here. The slope is undefined. The original function is continuous but not differentiable at 0. So we actually haven't found the derivative, but we did graph the derivative. By the way, I think it's worth noting that if this absolute value would have opened this way instead, if this would have been a positive absolute value of x, then instead of having the lines that are doing this for the derivative, they would have been switched. Okay, let's think about this logically. Notice negative slope, positive slope, so below the x-axis, above the x-axis. Just worth saying. Okay. I think it's also worth finding the actual derivative of the absolute value, and part of that comes from finding what this function really is. I think it's really worth noting that an absolute value function is really a piecewise function. And here are the two pieces. We have a piece that is below 0 and a piece that is above 0. And we are dealing with the original function here, which does exist at 0. Therefore, one of these is equal. It doesn't really matter which one because they meet. So I'm just going to give it to the greater than. So the line that is, well, this piece below 0, x value is less than 0, is going to be simply the line x. It's 1x plus 0. Y-intercept is 0, slope is 1. Here, the line is negative x, so negative x plus 0. So when I find the derivative, which to be consistent, I will write in red, I'm finding the derivative of a piecewise function, and that piecewise function still has two pieces. The slope of this first piece is 1, and this applies for x values less than 0. The slope of this piece is negative 1, and it applies for x values greater than 0, but not equal to, again, here's why, the slope technically does not exist at x equals 0. So we can't say that the derivative exists at 0. It does not. All right, now we get to some tricky ones. Well, tricky, but not tricky. Let's graph this. And when I graph this, I'm actually going to plot some points. Don't have a calculator on me at the moment, but I think we can figure this out. Let's just start by plugging in 0. When I plug in 0, I get 0. There we go. Let's figure out what happens if I plug in a 1. If I plug in a 1, I have negative 1/2 minus 2. That would be negative 2.5. So that dot is a dot. Good to know. If I plug in positive 2, I'm subtracting 4 here. Plug in a positive 2. I will have minus 4 here, 4 here, 4, 2, negative 6. 1, 2, 3, 4, 5, 6. Am I right? I think so. All right, if I plug in a negative 1, then I'm adding 2 here. If I plug in a negative 1 here, then I will have negative 1/2 plus 2, that would be positive 1.5. We're going somewhere with this, trust me. Let's plug in a negative 2. Negative 2 here is going to go so positive 4. Negative 2 here is going to be 4 and then 2, negative 2. So negative 2 plus 4 is going to give me 2. Oh, this function's just about to turn around. There we go. And just because I feel like continuing to plot some points, there's symmetry to this. That's the vertex, by the way. There we go. And that is it. Let me make sure I'm right. If I'm wrong, then we're going to have a mess, aren't we? Especially because I'm doing this with an ink pen. So if I plugged in, I'm going to grab some scrap paper. Give me just a second. Actually, no. I found a whiteboard right beside me. Oh, goodness, yeah, I'm right. Just look at what I'm writing on the board. There we go, yeah, I'm right. That is indeed the vertex. I was making sure I didn't miscalculate something in my head. So this is my parabola. This one's gonna generate a lot of conversation as we talk about it in a video where you don't get a chance to talk. So, okay, never mind, no conversation. It's more of a monologue, but there's the original function. Now let's graph the derivative, and this one, I wanna be really careful that I graph it correctly, because if I don't, then something's gonna be terribly wrong. So, negative 2, slope is negative 1, so we're gonna do this, yeah. There we go. All right, I'm gonna slide the paper for a second so this stand that's holding the camera doesn't get in the way. I say camera, it's really my phone. Okay, what do you notice? What do you notice? This one's gonna be worth a lot of discussion right here. All right, let's focus right now just on the parabola. So as I throw my hand down and I talk about these for just the next few minutes, for the next few seconds actually, I'm just going to be talking about the parabola. The parabola is increasing for this interval and decreasing on this interval, okay? I think that's worth noting. And so I'm gonna write a few things down in green that I think are worth saying. So the function is increasing for negative infinity to negative 2, and the function is decreasing for negative 2 to infinity. Again, from here to here, negative, I'm looking at blue, negative infinity, x value, negative infinity to negative 2, increasing, from negative 2 to infinity, decreasing. Okay, good to know, fantastic. Related to that, now let's shift our eyes towards red. The derivative is positive for what x values? Negative infinity to negative 2. Not a coincidence. Okay? I want you to notice the correlation between these two things that were written right here. These two things are essentially the same. The function is increasing, therefore the derivative is positive. You knew it, but now you're seeing it differently. Blue increases, red is positive. Oh, but red's going down. No. I'm not talking about whether or not red is going down. That actually would be a second derivative issue, and we'll deal with that in a minute on this problem, even though it didn't ask us to do so. I told you this was a good problem. It's good and juicy. Blue increasing, red positive. Let me rephrase that. Original function increasing, derivative positive above the x-axis. The derivative may be decreasing, but the derivative is positive, okay? So let's keep writing. The derivative is negative from negative 2 to infinity, and that makes a lot of sense because, here it goes, decreasing original function, negative derivative. Okay, you want to talk concavity? I sure do. Let's find the next derivative, and I'm going to do that one in purple, and I hope you can kind of see the contrast. I've used purple a little bit here, so there's that. So f double prime would be negative 1. So now we're graphing the second derivative. It's getting a little sloppy. I know there's a lot of stuff going on here, so if you want to just ignore the words for just a minute and look at the graph, blue function, red derivative, purple, hard to see, but second derivative. The graph, original graph, blue parabola, is concave down, always. The second derivative is always negative, not a coincidence. Isn't that lovely? I like it too. Okay, let's take this idea and go a little further with it. These are going to extrapolate on those ideas just a wee bit more. So let's graph original function in blue, cosine, no, cosine's over here, sine, 0 to 1 to 0 to negative 1 to 0. Okay, this is the way sine works. And if you're singing the song that we've consistently used in your head, then actually it's kind of working backwards. So sine counts back with 1 square root 3 over 2 square root 2 over 2, 1/2, then 0. That's what this is. If you're singing the song in your head, sine counts back with 1. Sine counts back with 1, that's here, and then it goes back. Okay, so we're not starting at 0. So in the song, we're not starting at 0, but we technically are starting at 0. Okay, here goes. We're going to graph cosine, but I'm going to graph cosine not realizing what the graph of cosine is. I'm going to just graph the derivative, okay? Watch this. This is so cool. The slope on this piece is positive. So I'm going to graph something above the x-axis. The slope for this is negative, so I will graph something below the x-axis. And the slope here is positive, so I will graph something above the x-axis. Now let's graph cosine. I also want to point out the slope of blue, of sine, at this point would be 0. Therefore, when I graph the derivative, I will cross the x-axis. We're going to come back and talk about that here in a second. The slope of blue, sine, is 0 here. Therefore, I'll have to come back and cross the x-axis. There's a lot to take in right here. We just graphed cosine. All right. Listen carefully. Blue increasing, red positive. Can I get wordier? Sure, why not? Blue increasing, red positive. Blue concave down, red decreasing. Okay, I'm now speaking in terms of the second derivative that's not showing up, but let's move on. Blue decreasing, red negative. Blue decreasing, red negative, but it's going up, but it's negative. Blue increasing, red positive. All right, let's talk concavity again for just a second. Blue, original function, concave down. Second derivative, negative. Second derivative is not showing, but original function, concave down. Derivative, decreasing, because the derivative of the derivative would be negative. All right, original function, concave up. First derivative, increasing. Let's move on. Now we're going to graph cosine, which we actually already have here. And now original function is going to be blue. Okay, I'm going to graph negative sign. So what I had over here that started is, excuse me, this is the graph of sine. This blue graph over here was the original function. Now it's the derivative, but it's negative. So everything that's going up then down is going to go down then up over here. So let's graph it, and then there we go. Let's talk about it. Let's do it, let's do it, let's do it. Original function, decreasing. Oh, let's go here. Original function, decreasing, derivative, negative. Original function, increasing, derivative, positive. Original function, concave down, derivative, decreasing. Original function, concave up, derivative, increasing. Original function, concave down, blue, down, concave down. Derivative, decreasing. Okay, let's back up for just a second and talk about a few important points. I'm pointing vaguely, let me point more clearly. I had a place right here at x equals -2 on this graph where the derivative was 0. That always corresponds to an x-intercept of the derivative. Let me say it again while pointing in a different place. Where a function has a derivative of 0, we know these as maximums and minimums on smooth curves. Maximums and minimums occur where the derivative equals 0, smooth curves particularly. So derivative equals 0, derivative equals 0, derivative equals 0, derivative equals 0, lines not worth talking about in this context, okay? Derivative equals 0 here, 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 here. Therefore, the derivative that we graph, for mine is red, will be an x-intercept. The derivative equals 0, touch the x-axis. The derivative equals 0, touch the x-axis. Derivative equals 0, touch the x-axis. Derivative equals 0, touch the x-axis. Okay, let's fill a few things in. If f is continuous for every real number x, then the derivative is always continuous, sometimes continuous, never continuous for every real number x. Every real number, we're just not playing with imaginary numbers, as fun as they may be. So if a function is continuous, think of a continuous function, like this one, or 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 this one. They're all continuous. Then the derivative is continuous. Always? Let's think of an exception, if possible. Original function continuous, derivative continuous. Function continuous, derivative continuous. Function continuous, derivative continuous. Function continuous, derivative. Oh, what color? Let's go purple. if a function has a discontinuity at x equals c, then the derivative has a discontinuity at x equals c. Always, sometimes, or never. Well, okay, if I were to put a hole in the graph, just right here, at that specific value, right there, then I could not have a derivative at that point. So if I was to graph the original function and it had a hole there, I better have a hole here. So this one would be always. Okay, now let's think back about the shortcut, the derivative shortcut. If f is quartic, that means it's to the fourth power, then the derivative is, okay, we had something to the fourth power, we take the derivative, now it's cubic. Okay, this part should go fast. If the derivative, if the function is quadratic, we get, whoops, linear. My aim was off. If the function is linear, then the derivative is just a constant. Not just a constant. If function, is cubic, then the derivative is quadratic. There we go.